Hi, can you hear me?
Good morning, sir.
Good morning. Just am I still audible?
Yes, sir.
Okay, let's start. So maybe first thing I want to do is just go over the test paper that was given last time. Some of the common mistakes that students have done in some of the questions I would like to point out. I have checked your papers. I'll keep them at the MPI office, and you can collect them anytime this week. For those who submitted the paper online, I will send it on Google Drive. Okay. Uh, but just to start with some general comments about how I think you should approach paper like this. So first thing I noticed, many students, the first section was numerical, so you were not supposed to actually show the working in fair. I mean, rough work is fine, but in fair you were just supposed to write the final answer and move on. But I think many students spend a lot of time explaining that, and I think that left you with less time for section B. Uh, so just keep that in mind for next time. That just write the final answer and move on. And in section B also, I feel that so this always happens that some students have the right idea, but the way they write the solution doesn't make it clear that you have understood everything logically. So I think wherever possible, I've left comments on your paper and just go through them and make those corrections next time. Okay. So try your best to explain logically what you are thinking, how you want to explain the steps and things like that. At the same time, don't overdo it also, in the sense, there are a few cases where many things were written which were not necessary. For example, in the first question, right, the question 5, that is 100 students are standing in the regular 10 cross 10 grid. Uh, I think many students had the right idea that we want to set up a coordinate system, right, with 0, 0 as the bottom left corner. So it is just enough to write that in one line that we are setting up a coordinate system such that the bottom left corner is 0, 0, and all the students have integer coordinates within the range 0 to 9. So it's enough to just write that and move on. So you are not supposed to explain every detail that this is the coordinate of the student and this is the distance between the students. It's not required. In the same way, same question again, we know for a fact that if any three students are collinear, then one student will go to block the line of sight for the other two. So that can also be explained in a much simpler language. So what I'm going to do is, even I have solved the same paper and I'll upload my sort of model solution for everybody. Note that this is not the only way, of course, to write the paper, but just to give an idea that if I were to write the paper, what would I write? I mean, we want to write everything that is necessary, but nothing that is more than that. So we just have to write the exact ideal set of things to be clear with what is your idea and things like that. So for that reason, I think yeah. So that is one thing which I think we will have to improve upon. A few other common mistakes that students had done, I think. So So I think question 6, the let B be an odd number and S be the set of all numbers with odd number between 0 and 2B. In that question, many students they directly state that with division algorithm, such Q and R will exist. And therefore R will belong to S because R is less than B. But the point is that R is given to be odd. So sorry, the set of numbers in S is given to be odd. So unless R is odd, it is not going to belong to that set. So I think that was one mistake that many students did. Uh, I think question 7, most people did get it. In fact, there are some interesting solutions which are there is some approaches that use strong induction, but in fact it can be done with normal induction as well. So that was interesting to see. And question 8. Question 8, actually, I think many people got stuck with trying very difficult things. So this often happens that you look at a question and you feel that you have to apply something difficult like Bezos theorem. You want to represent the GCD as a linear combination, but this was actually one of the simplest questions in a lot of ways, because all it was about, if D divides A and D divides B, then D divides A plus B or A minus. So that alone was sufficient to solve that question. So anyway, I'll send you my sample solution for you so that you have some idea of how you can approach these questions. But right now, I just want to go through the solutions of these questions to explain not what is the solution, but actually what is the motivation behind each solution. So I think that is very important to understand.
Sir, the papers are at MPI office of Siddharth Towers.
I still have them with me, but I'll keep them at Siddharth Towers today or tomorrow. I'll just drop a message on the group.
Okay, sir. Yes, sir.
Sorry, I'm having some difficulty connecting my tablet. Oh, I realized my mistake. Sorry. Okay, actually, unfortunately, my tablet is still not working. But while we are waiting, let me just give a problem to think about. So you looked at question 8, right? So question 8 was more generally with the Fibonacci sequence defined. GCD A comma B is equal to that GCD Fn A plus Fn minus 1B. So I would like us to think about the most general question of that sense. But suppose you take any linear combination of A comma B. Let's say PA plus QB and RA plus SB. Okay. And the question is, what is the necessary and sufficient condition on PQRS such that for all integers AB, GCD of A comma B will be equal to the GCD of those two linear combinations. Okay. So I don't know if anybody has already thought about this question and you know the answer, but if not, then this is something you can quickly give some thought to. So did you understand the question? That, I mean, basically, I want you to think about what is so special about the Fibonacci number, that Fn minus 1, Fn plus 1, and Fn. Whatever those numbers were given, are they the only ones which have this property, or is there some general pattern which, if some numbers follow that pattern, then they will have the same property? Okay, so while you're thinking of that question, let me just try and restart my tablet. Can you see my screen?
Yes, sir.
Yes, sir.
Okay, so just to repeat the question which I mentioned just now. So find the necessary and sufficient condition for integers PQRS such that, and this is the important part, for all integers A and B, GCD of A and B should be equal to GCD of PA plus QB RA plus SB. So the question that we had asked in the test was dealing with I think Fn minus 1, Fn plus 1 and Fn. So this was a special case of PQRS which was satisfying this property, but what is the general condition for such numbers? That is something that you can think about. Okay. But anyway, I just put this as a problem for you while I was connecting my tablet. So you can continue to think on this problem, and if you have a solution, you can send it to me. It's not that difficult. So, but anyway, so I want to return to the question paper discussion. So starting with the first question. So question one was of ABPQ, the 4 points, such that triangle APQ and BPQ have the same 9-point circle. So what was the main idea here for those who have solved the question? When two triangles like this have the same 9-point circle, what happens?
They will have the same circumradius, and they like line AB will be perpendicular to line PQ.
Yes, not only that. So they form what is called an orthic configuration. Have you heard this term?
Yes, sir.
Where basically every point is the orthocenter of the other 3 points. So basically what you get is, if you have this triangle, now this I'm taking a general triangle, and you consider the orthocenter. So this was the thing. This was kind of reverse engineering, something that you all know already, or I hope you must have studied this when you studied 9-point circle. That basically H is the orthocenter of triangle ABC. In the same way, A is also the orthocenter of triangle HBC, correct? And as a result, what happens? We know which points lie on the 9-point circle. So the midpoints of the side. So midpoint of side BC, D, these midpoints. The midpoints of HA, HB, HC. So these points, and the outfit of the altitude. So these are the 9 points on the circle. So basically, if you consider the 9-point circle of triangle HBC, it contains the exact same points, just interpreted differently, because now the midpoint of HB and HC is no longer the midpoint of the orthocenter joined to the vertex. It is the midpoint of the side. So the midpoint of side HB is this point, and now the midpoint of the orthocenter of HBC, which is A, joined to H. So that is this point. So the points are simply exchanging roles, but it is the same set of 9 points. Okay. So therefore, all these 4 triangles, ABC, HBC, HCA, and HAB, they'll all have the same 9-point circle because they are all the same 9 points, just labeled differently. Okay. So in case you're not aware of this property, or maybe you can take a look at this later. But this is sort of the forward direction. What I asked was kind of the converse, that if you have some triangles, ABC and I think APQ and BPQ, okay, where their 9-point circles is given to coincide, then what can you say about them? So you can work out that you can prove, in fact, that, I mean, first thing is, of course, they have to have the same foot of the altitude. But starting from that, you can also work out the other details and show that B has to be the orthocenter of triangle APQ. Okay. So this was what the question was about actually. And once you know that, then the rest is kind of direct calculation, because I think everybody knows the 9-point. Basically, the length of AB and the length of PQ have a very direct connection, because AB is twice of this OD, and then this ODP is a a simple like 90-degree triangle. So then in ODP, basically we all know that PD square plus OD square is equal to OP square, which is R square. So in other words, the AB, PQ, and any measure of the circumradius, either the 9-point circle radius or the circumradius. So these form what is called a datum. So datum means that if you know any two of them, you can find the third one. Okay, so that was all the question was about. But I mean, important to understand what is the motivation that you should look for in this question. First thing you have to notice in a question like this is that you have a lot of degree of freedom. See, there are 4 points given in the question, and the information given is very less. So, in fact, there is not a unique triangle which has these properties. You can have a whole family of triangles, and you are free to choose any representative of that family which is easiest for you to compute. Okay. So, for example, you could consider a isosceles triangle if that is convenient to you. So, I mean, you can do a lot of simplification that way. And like any case which you can solve easily, you can do that and find the answer. Okay. The question 2. So question 2 has actually multiple approaches. One was I saw because like fortunately you had written the explanation, so I understood that basically PRRT has been used by many students. So possible rational root theorem to figure out which are the candidates for solutions, and then you just try them one after the other, which is fine. But in some cases, like here I use very small numbers. If there were much larger numbers, it's hard to apply PRRT and try all the values. So the other approach, which I would say is more scalable, is the fact that if two polynomials have a common root, let's say alpha, which means that P of alpha is 0 and Q of alpha is also 0. Then any combination of P alpha and Q alpha, the Px and Qx polynomials will also have the same root, right? So like Px plus Qx, Px minus Qx, or any other linear combination of these two will also have the same root, because here also P alpha plus Q alpha is going to be 0. And you have to exploit that fact to reduce the degree of the polynomial. So P of x was given to be a 4th degree polynomial, and Q of x was given to be a 3rd degree polynomial. So you want to eliminate the x raised to 4. So what you can do is P of x minus x times Qx. Okay. So if you do that, basically the x raised to 4 will get cancelled, and you will be left with, I think, another 3rd degree polynomial. And what is important to note again is that if alpha is a root of P of x and Q of x, then it is going to be a root of R of x also, right? Because R of alpha is nothing but P of alpha minus alpha times Q of alpha, which is going to be 0. So there's a whole family of polynomials you can generate starting with a given set of polynomials, and how the roots are related to each other. And so, I mean, now R of x has a cubic. We still don't know how to solve a cubic, but you can now subtract Q of x minus R of x, and to get the S of x, which will be a quadratic. And once you have the quadratic, you can find its roots. The only thing you have to check is that whenever S of x has some roots, let's say alpha and beta, one of them may be a common root of the original polynomial, but it is not an if and only statement. So you have to check manually which of these are actually roots of the original polynomial, but you can substitute and check that. And turns out both of them are the roots of Q of x. So once you can factor them out, you can get all the roots of P of x and Q of x. Okay. So the main idea here was the linear combination of the various polynomials. So linear combination and how two polynomials can be added and subtracted, and the relation of the roots with that. So how roots are related to polynomial arithmetic. Because there are some other tricks also in some questions, like sometimes you can see reciprocal kind of equation. So if Q of x has given some roots alpha, beta, gamma, you can consider the Q of x, which is the polynomial of the reciprocal, and you have to multiply it with some suitable power of x to make all the degrees positive. So this will have the roots one upon alpha, one upon beta, one upon gamma, things like that. So some tricks like that are involved in such questions. Okay, question 3. I think pretty much nobody, I think 1 or 2 students only were able to solve this question. Maybe it was a bit harder in that way, but it is not that hard once you understand what's happening. So the equation given is xt plus 1 is equal to 2xt plus yt, and yt plus 1 is equal to xt plus 2yt. So, and we were asked about some GCD of x4 or y4. This was given, and what is the GCD of x0, y0? Like, what is the possible range of these values? So, one way to do is you directly find x4 and y4 in terms of x0 and y0, and I think many students had done that. So you can write x4. I think x4 is 41 x0 plus 40 y0, and y4 is 40 x0 plus 41 y0, something like this, and then you can try to see the relation between that. There's one more approach where you go one step at a time. So you try to connect the GCD of x4 y4 with just the term before, GCD of x3 y3. What are the possibilities of these two GCDs? Okay, you can do it one step at a time, and that is because this is the recurrence given to you. So in this recurrence, what do you know? So if I call this GCD as D1 and this GCD as D2, okay, or I mean in general, let the GCD of xt comma yt be denoted as D1, and the GCD of the next term be denoted as D2. Then what is the connection between D1 and D2, which you can deduce from these equations? So firstly, D1 divides both xt and yt. So D1 is going to divide any linear combination of the two. So I think everybody agrees that D1 is going to divide D2, correct? And conversely, what can you do about figuring out what D2 divides? So D2 divides 2xt plus yt. D2 divides xt plus 1, which is 2xt plus yt. And D2 also divides xt plus 2yt. So if I just add these, I'll get D2 divides 3 times xt plus yt, right? And I can then subtract this from the given equations, like these two. Oh, sorry, and I can also subtract them. Sorry, I realized this. So just as we're adding them, I can subtract the two equations, and I'll get D2 divides the difference, right? So in fact, yeah, this is actually more useful. So because I can add this xt minus yt to the original equation, and I'll get D2 divides 3xt and D2 divides 3yt. Okay. And what can I say about 3xt and 3yt? Their GCD is going to be thrice the GCD of xt and yt, right? So GCD of 3xt and 3yt will be 3 times the GCD of xt and yt, which is thrice D1. So basically what you have is D1 divides D2 and D2 divides thrice D1. So this constrains D2 to lie in the range D1 and 3D1, right? So there are only two possible values for D2. So D2 can be either D1 or D2 can be thrice D1. These are the only possibilities for D1, which means from one step to other, the GCD can only get multiplied by 3 or remain constant. So if I know that GCD of x4 comma y4 is 54, so if I were to work back 3 steps, so x3, x2, x1 and x0, at each step as we go back, only two things can happen. Either the GCD will stay constant all the way, so it will stay constant all the way down to the first term, or it can reduce by a factor of 3. So from 54, it may go down to 18, it may go down to 27, 6, and it may go down to 2. And once it goes down to 2, there is no way but for it to remain constant. So these are the two extreme cases possible. Either it will remain constant or it will keep reducing. So therefore the range is 2 or 54, and it's not hard to come with some numbers which satisfy both extremes. Yes, Gaurav.
Yes, sir. So is it possible that a number like kind of for some time it, like for example from 18 to 54, I say 54 to 18, and then it remains constant without fully being divided by 3?
Yes,
Like, is that
yes, that is
possible?
possible. Yes, yes. So in fact, somewhere in between is also possible, that it may go to 18 and then remains 18 till the end. That is also possible. But anyway, because we are interested in the minimum and maximum range, so that's why I took these extreme examples. But something in between can also happen. Okay. So I think if you want some number, I don't remember exactly, but I think
I think 4 and 6 works because I think I checked that in the paper.
4 and 6. Okay.
Yes, I think that works.
Yeah, 4 and 6 or 4 and 2, something like that works. And I think the other pair was 4 and 54 plus 4, basically 58. So this is the case where this something like this happens. Oh no, sir. No, I think this is
Sir, 54 and 108. That way GCD will always be 54.
54 and 1. Okay. Yeah. If you start with the GCD, but how are you sure that up to x4 comma y4 the GCD remains 54? It doesn't keep increasing.
Sir, it can't increase. No, it can increase.
Yeah, actually I worked out the numbers. I forgot now, but anyway, I'll include them in my sample solution.
Actually, sir, if I don't know if this is an example, but we can directly prove that the GCD of x1 x0 x0 comma y0 cannot be greater than the GCD of x4 comma y4, because if GCD of x0 comma y0 is greater than GCD of x4 comma y4, then if that is d, then d will divide x1 y1 x2 y2 and all of them.
Yes.
So
Yes, correct. Yeah, that is true. In fact, what we have shown is even stronger, right? What we have shown is that in each step the GCD can remain constant or the GCD can go to thrice.
yes, sir.
So there is no way for it to decrease actually. Girl, you want to add anything?
No, sir, nothing, sir.
Okay. Okay, so this was question 3. So, I mean, understand the approach that you can think of that. Try to do it one step at a time. So, how to relate one GCD to the previous or the next term. That was the idea. Question 4, I think I can skip. Most people did get it, so there was nothing in that. And I mean, we are not formally covered how to find the first solution using Euclid's algorithms. That is something we'll do today. But the numbers were small enough that you can guess and find out the initial solution anyway, and then you can get the whole family of solutions. Okay. Okay. So in question 5, I think most people, as I said, got the idea correctly that what you're supposed to approach it with, but how you write it properly was the whole trick. So how can you be efficient in presenting that so that you have to write the what is the minimum necessary, but nothing more than that. Okay. So I won't write the whole solution here. I'll just send it to you. But for those who didn't get the problem, and basically it is just that if you consider it as a coordinate system with the bottom left student being 0, comma 0, then any other student whose coordinates are co-prime numbers. So if the GCD of A, comma B, and by the way, this is why I prefer to write GCD AB. I mean, some literature just uses the bracket notation to denote GCD, but this is precisely the question where the bracket can refer to the point coordinates or the GCD. So there is some ambiguity there. So just write GCD A, comma B is 1. So if the GCD is 1, unfortunately, so the point of GCD is not 1. Okay, then it will have a direct line of sight with the origin because no other point will come in between. And I mean, just to illustrate, the best way to quickly finish this problem is just consider the equation of this line. So the if A, comma B is the coordinate of this point, then this line is simply what A Bx is equal to Ay, right? So if you just consider this as a Diophantine equation, and you can rearrange this on one side, so Ay minus Bx equal to 0, then you can apply the entire theory of Diophantine equation that you have developed. That we know the initial solution is 0, comma 0, and so the entire family of solution will be 0 plus the GCD is 1, so therefore 0 plus b times t and 0 minus 8 times t. And if the GCD is not 1 also, if the GCD is d, then this will be bt times upon d. So this is the simplest way to cover all the cases without having to do any like case by case analysis is not required. Okay. So I'll show you, I mean, at least how you can write this in the simplest possible way. The answer is, I think, 57, by the way. Okay, question 6 is actually, this is typically how I took division algorithm and just change it a little bit. So understand that there is not one division algorithm. What we have as the standard division algorithm is just one division, but the set of remainders can be modified quite interesting ways. So in fact, in general, the set S simply has to be some set of what is called complete set of residues modulo the divisor. Okay. So we'll look at this in more detail today. So complete set of residues. in this case modulo b, which means that it has all the possible remainders which can occur and no two elements are congruent to each other. So in the given example, it was 0, 2, 4. Oh, sorry, it was odd numbers, right? 1, 3, 5, 7, up to 2b minus 1. So this was the set S that was being considered. So it's enough to note that basically no two elements of this set are going to be congruent modulo b. So if you have any R1 and R2 which belong to this set, then R1 minus R2 will never be a factor, multiple of b. And S has all such elements. So the size of S is the number of possible remainders. So if these two conditions are satisfied, then S can be any set. Okay, that is something that we see today. Question 7. I think question 7 also most people did get. So I'll just indicate the alternate proof that was there. One approach which many students have used is strong induction, because finally the claim turns out to be Fn square is equal to or minus Fn minus 1 Fn plus 1 is minus 1 raised to n plus 1. So minus 1 raised to n plus 1 means this is going to alternate between odd and even numbers. So that's why the natural induction you might think of is you have to go from Fn minus 2 to Fn, and which is perfectly fine. So you can do that. You can show that these two are equal basically. And when you show that these two are equal, obviously the terms are going to alternate starting from 0. So that is perfectly fine way of doing this. But some students did a very interesting approach. You can do a simple induction also. You can connect this to the previous term, Fn minus 1 square minus Fn minus 2 Fn. And that was an interesting manipulation. I also hadn't thought of that. So let me try to recall it exactly what it was. Yeah, I think they took this Fn. See, the first instinct that all of us have is to break this replace this Fn with Fn minus 1, Fn minus 2, and expand that bracket and do things like that. But I think what they did is, what if we started expanding this term first? Okay, so we'll get Fn square minus Fn minus 1. So what you get here is, so you see how nicely it is being arranged for the alternation, that while trying to find a value of Fn square, you have got a minus Fn minus 1 square, which was the induction hypothesis with normal induction. So now this minus Fn minus 1 square can be replaced with the suitable term from the induction hypothesis. So if we assume that Fn minus 1 square minus Fn minus 2 Fn is equal to minus 1 raised to n. Okay. So then this will be equal to Fn square minus Fn. So minus Fn minus 1 square is nothing but okay. So minus Fn minus 1 square can be replaced by this. So you have got the answer here now actually. So if everything has cancelled out, we are done. So we just need to check that all of these things cancel out. And that, do you see that it's already happening? Because Fn is common in everything. So surprising, without expanding Fn square, you are getting the answer. So this was a very
Actually,
nice.
it is minus Fn minus square is minus 1 raised to n plus 1 minus Fn minus 2 Fn.
Oh, okay. Oh, sorry, I have to, yeah, 5 is minus. Okay, yeah, so therefore, inside you get Fn minus 1 minus Fn minus 2 plus minus 1 raised to n plus 1. And then this term is exactly 0. Okay, so yeah, this was a very nice idea. And in fact, the fact is the Fibonacci numbers have a lot of recurrence relation between them, which can be derived from just the starting point. So I'll encourage you to find out more properties about the Fibonacci numbers. Okay, and question 8, I think already I've given you the sort of superset of that question, what you're supposed to do. And the idea is simply that if D divides A and D divides B, then will D divide any linear combination of them, including the whatever is 2A plus B and 3A plus 2B. But of course, because you have to show that GCD is equal, you have to show the other way around also. That if D divides 2A plus 3B, and d divides 3a plus 2b. It's not hard to use the linear combination of these two to get back a and b. Okay, so it's like a two-way operation. And same happens for the Fibonacci numbers. In fact, I mean, in the question paper, I did realize that the odd number condition is not required. So, so that for any natural number n, that Fibonacci equation holds true. Okay, so yeah, that was about the paper in general. Uh, as I said, wherever possible, I've written quite detailed comments on each of your answer sheets to indicate what can be improved in terms of writing and things like that. So as I said, pay attention to both things. There are cases where things which should have been written but you did not write, and that gives the examiner some ambiguity to understand whether you understood it or not. And there are cases where you unnecessarily written too many things which are not required, and that eats up your time. So you could use that time to solve something else. So pay attention to both kind of mistakes. Okay, but I think on the whole it was a good paper. Everybody got to learn something. See, the good thing is that there is nobody with 0 marks and there is nobody with 100 marks, which means everybody did something right and everybody did something wrong. So, so that's the positive you can take from. Actually, there is a sort of statement. I don't know if this is official. How we have fundamental theorem of arithmetic, fundamental theorem of this. In that way, I have a fundamental theorem of entrance test, and that is in any entrance test, there is always going to be a strongest student and a weakest student. And that doesn't seem like a big statement. Obviously, that is going to be true, but just think about what that means. That suppose you have a room full of Nobel laureates, okay? Everybody is a Nobel Prize winner, and you make everybody give a test. Still, somebody is going to be the weakest student in that class. Doesn't mean that student is bad. He's still a Nobel laureate, right? Conversely, you can take a group of students who have all failed class 10 and ask them to write an exam. Somebody will be the topper in that class. Doesn't mean he's good. He's just better than the others. So it is all going to be relative no matter what you do. So I mean, don't compare yourself with others. Compare yourself with what you could have done. So is there anything that you could have improved? Look at that and try to improve it in the next exam. So I'll keep having these exams once every 4 to 5 weeks, as and how we cover various topics. Okay. Okay, so then coming back to this original question, find the necessary and sufficient condition. So what should this PQRS be such that this is a two-way street? And importantly, for all integers a and b, this should happen. So firstly, is it clear that clearly any PQRS will not have this property? There has to be something special about PQRS. Because very simply, you can take PQRS all equal to 2, for example. Clearly, GCD of AB is not going to be equal to GCD of 2A plus 2B and 2A plus 2B. This is not going to be the case, right? Because clearly there is a power of 2 being added here, which may not AB may be odd numbers, for example. So PQRS cannot be any numbers, that is for sure. And what else can you say? Let us say the GCD of A and B is D1, and GCD of the PA plus QB RA plus SB is equal to D2. No matter what PQRS, do we all understand that D1 has to divide D2? Because D1 divides AB, D1 will divide any linear combination of AB. So D1 will divide PA plus QB and RA plus SB. And then from theorem we had done last time that D1 has to divide the GCD of those two numbers. So D1 divides D2. So half the battle is done, right? So now the only thing I have to check is what is the necessary substitution condition such that D2 divides D1. Okay. So what is the condition such that D2 divides D1? Because if D2 divides D1, then this will imply D1 and D2 are equal. So if I denote PA plus QB, the whole thing as C. Okay, let me not use C and D. Maybe E and F. E and F. Okay. Can you write A and B in terms of E and F? See, the equations you have as E is equal to PA plus QB. And F is equal to RA plus XB. So these are equations. If you know A and B, you know how to get E and F. Can you write the reverse equations?
Yes, sir, using Kramer's rule.
Yeah, Kramer's rule, or simply, I mean, solve just the way you solve any simultaneous equation. So, for example, let's say we want to eliminate B. So we'll multiply the first equation by S, second equation by Q, and subtract. Okay. So B will get cancelled, and what we get is ES minus FQ is equal to 8 times ES minus QR. So therefore, A can be written as ES minus FQ upon PS minus 2. And specifically, I mean, it doesn't make it clear that actually here we are treating A as a linear combination of E and F, right? So let me write it that way, that this is E times PS minus QR minus F times Q upon PS minus QR. At this point, we don't know whether these are integers or not, but we have just written the expression. So A can be written in this way, and similarly B can also be written. So what will B be equal to? Something E minus something F. Right?
EF minus ER upon PS minus QR. So P times F by PS minus QR minus E times R by PS minus QR. No, sir, opposite. Minus plus is opposite.
Oh, so this will minus R here, and
Plus F. Yes, sir.
okay, fine. Yeah, actually, let's put the plus sign here. So if whatever I've written in the brackets here, suppose all of these are integers, okay? Suppose these are all integers, the coefficients I'm talking about. Then can we say that d2 divides d1?
Yes, sir.
Because see, d2 divides e and d2 divides f. So d2 is going to divide any integer linear combination of them, right? So if these yellow highlighted brackets are all integers, then this will imply that d2 divides a and d2 divides b. So does that give some idea what might be the necessary and sufficient condition that PQRS have to satisfy?
PS minus QR should divide all of PQRS.
Okay.
So, but I don't know if this is necessary or not.
We don't know that this is, we have not proved that yet.
It is sufficient, but it is.
It is sufficient, but it is not. We don't know if it's necessary or not. But I'm still waiting for you to think. Is that the best way to express what is the condition? If you want to make a guess, what is the condition? See, what needs to happen, if that happens, then obviously these are all going to be integers. What if PS minus QR is equal to 1 or minus 1?
Yes, sir.
If it is one, then it can happen.
The modulus of PS minus QR is equal to 1. If that is true, then obviously everything is an integer and we are done. And now the question I'm going to ask you is the what I had asked in the question, that P, Q, R, S, what are they? So P was Fn, Q was Fn minus 1, R was Fn plus 1, and S was it. Do they satisfy this condition?
Yes, sir, because which minus 1 raised to n in the previous question we solved.
Yeah. So actually question 7 was setting up this property. Question 7 was exactly saying that prove that PQ minus RS is equal to 1, where PQRS are defined this way. Okay, so that was kind of a indirect hint in question 7 being given that the condition is a modulus of PS minus QR is equal to 1. Okay. So right now we have only claimed or proven that if PS minus QR is equal to 1, then we can guarantee D1 equal to D2. But why is this compulsory? That what will happen if PS minus QR mod is not 1? In that case, why will D1 not be equal to D2? That is still unknown. But I leave that as exercise for you to try. I don't want to reveal the answer. It is doable. It is actually kind of simple. So if you assume that this is not equal to 1, if you assume it is some t greater than 0, and then you can get a contradiction from there. So I'll leave it for you to try it out. But this is a very interesting condition, right? PS minus QR mod. And by the way, do you know if you know what is determinants? So basically, this is PS minus QR can be written as in a determinant form, so PQRS. So this determinant has to have a modulus of 1. That is what we are talking. Okay. So returning back to the theory that we are doing. So I mean, we are almost done with the divisibility topic. Just the Euclid's algorithm I had forgotten to cover last time, so I will talk about that. And then we'll move on to. So in Burton, actually, after this, there is a chapter 3 which is prime numbers, but I'm going to rearrange things. I want to do congruences first before we do prime numbers, because I feel that is a much more natural topic to cover, and also much more useful also in some ways. I think what prime numbers topic covers are things which you already know. I think you all know that primes can be used to factorize numbers and things like that. So purely from the objective of developing the problem solving tools, I think congruences are more useful. So that's why I'm doing that first. So Euclid's algorithm, I think students may already know what is Euclid's algorithm, but basically it's algorithm to quickly find the GCD of two numbers. So if given some numbers A and B, we want to find their GCD. And the pretty much the only property we are looking at here is that the GCD of A and B is equal to the GCD of A comma A minus B. Okay. And this I think everybody can figure it out how to prove this. It's quite straightforward actually. So which means that we can subtract one copy of the pair from the other number, and we can keep doing this. So nothing is stopping us from doing this A minus 2B, A minus 3B, and keep on. So in general, we can go up to as many terms as we want and keep on going. And what this will achieve is it is going to reduce the, without changing one number, it is going to keep reducing the other number. Oh, sorry, let me write it as B comma. Okay, so I'm subtracting a copy of B every time from the second term, and I can keep doing this. And we can keep doing this until this becomes negative and also keep increasing in the minus infinity, but that is pointless. What we achieve is that if this number is as close to zero as possible, then that can be used as a starting point to restart this chain. So the idea is that if by division algorithm we know that there exists Q and R such that A is equal to QB plus R, and R is between 0 and B. So R is the remainder. So therefore, from this property, what we know is that GCD of A comma B will be equal to GCD of B comma R. And that's the only thing we want to keep applying. So starting with the initial numbers, so let me call the first number as A1 and A2. So instead of calling them A and B, I'm just calling that A1 and A2. So you can write A1 is equal to some Q1 A2 plus R1. Okay. So where R1 is between. So here I'm dividing A1 by A2. And what we know from the theorem which we did just now is that the GCD of A1 and A2 will be equal to the GCD of A2 and R1. So we repeat this chain and note the fact that this 0 less than R1 less than A2 means that R1 is the right candidate to be the next divisor. So in the next step, I'm going to divide A2 with R1. Okay. Oh, sorry. Actually, that's why I created this notation. Let me not call it R1, let me call it A3 to indicate how this chain is working. So the numbers are going to keep decreasing. Okay. So every time we take the new remainder and turn it into the divisor. And so on and so forth. Oh, by the way, it's not less than, of course, the remainder can be 0. So when will this chain stop? See, the only
So when
condition
AI
that,
becomes 0.
correct, because the only condition that division algorithm puts on us is that divisor cannot be 0. So at some point, let's say at the end step, you got A is equal to Qn, An plus 1 plus An plus 2. And let's say this An plus 2 is 0 now. So now we cannot repeat this step. We cannot go An plus 1 is equal to 2n plus 1, An plus 2. This won't work. So we have to stop here. And so when we say An plus 2 has become 0, which means that this term is no longer present. So it is simply An is equal to Q1 into An plus 1. And if that is the case, and as we said that the chain of GCD is going all the way from the start to the end. So GCD of A1 and A2 will be equal to GCD of A2 and A3, which is GCD of A3 and A4, all the way to the last pair. So this is going to be the GCD of the last two terms that we wrote, An and An plus 1. And if An plus 1, the remainder is 0, which means that An plus 1 divides An. So this means that An plus 1 is itself the GCD of these two numbers. So basically the last non-zero remainder that you get, An plus 1 here, is the GCD of your original pair. Okay. So this is the Euclid's algorithm, so that you don't have to know the prime factorization of the numbers. You can still find a GCD very efficiently. So the same idea can be actually used to figure out the what are the coefficients of the numbers which can be used to generate the GCD through linear combination. So like what Bezos theorem used to tell us is that if the GCD of two numbers is D, then there exists some integers x and y such that D can be written as a linear combination of x plus dy. But that was only existence. It never gives a way to actually find what is x and y. But with Euclid's algorithm, we can actually find that, because what you can do is we can actually reverse this process from the last term to the original term, and in each step you will actually find what is the GCD in terms of those two terms. Okay, so I mean, best way to show it is with just illustrating some examples. So we may take some big numbers and we'll see how we can use this approach to find the GCD as a linear combination of those two numbers. So let's say take some numbers like 52 and I don't know 98. Okay. So first thing is we want to find the GCD using Euclid's algorithm. So 98 is 1 times 52 plus what is the remainder now? 46. So now the new so 52 and 46 are my new candidates. So now I have to try and divide 52 with 46. So 52 is 1 times 46. And see, for the most part, the quotient gets ignored. If you only want to find GCD, the quotient doesn't have much role. But if you want to actually find the linear combination, then the quotient will matter. So 1 plus 1 into 46 plus 6. So now 46 is equal to 6, 42 plus 4. So now 6 and 4 are my new. And while you can stop at any time once you know, once the numbers are small enough that you can get the GCD, right? So here we already know that GCD of 6 and 4 is 2. So if you only want to find a GCD, we can stop here and just declare the answer that the GCD of these two is 2, and we are done. But here we want to find a linear combination as well. So I am continuing with this pattern. And so the last term is 4 is equal to 2 into 2 plus 0. So this is where we stop. And now from here onwards, I want to start reversing the process from this step. So from this step, if I just take everything to one side, see, I can write this as 2 is equal to 1 into 6 minus 1 into 4. Okay. So I know how to 2 is the GCD of 6 and 4, and I also found the linear combination of those two. So I just have to keep going back up this chain. So now using this the equation before that, so using this one, so using this equation, I can substitute 4 with everything on this side, right? So this can be written as 1 into 6 minus 1 into 46 minus 7 into 6. Okay. And here is in this again, regrouping 6 together and 46 together so that we can continue this chain in the upward direction. So this is nothing but 1 into 46 plus 6 into 6. Okay. There's a mistake. So this should be 8. Okay. And so on and so forth. So now here I have to replace 6 with this term. So this is going to be minus 1 into 46 plus 8 into 52 minus 1 into 46. So again, 46 will get combined. And you know, it's surprising. In general, you don't expect such big numbers. The product of two big numbers minus subtracted with each other, giving a very small answer like 2. But by Bezos theorem, we know that such numbers have values. And I think only one more step is written. So now I substitute uh, 52 or 46 from this. So 46 is 98 minus 52. And then you can finally rearrange this into get 52 into something plus 98 into something. Okay. So this is how you can use this chain of division algorithms to substitute back and get the original two numbers like 52 and 98. And what is the linear combination of those two numbers, which will give you the answer. Okay, I hope you are following this. So by the way, this is one way to apply a division algorithm, but in an exam, you can be actually smart and save some time in calculation. For example, notice here, there was no reason to take the remainder as strictly lying between 0 and the divisor. What if I replace this first step with something different? So instead of writing 98 is 1 into 52 plus 46, you see 52 into 2, 104 is a much closer multiple to 98, which will get my modulus down much faster, right? So why don't I write 98 as 2 into 52 minus 4? So now I can consider 52 and 4 as my new pair. And oh no, not minus.
I is 6, right?
Minus 6. Sorry. Okay, so now I can consider 52 and 6 as my new pair. So I can get the numbers down much faster. Okay, so you can use steps like this. So now 52 is nothing but to be 6 8 are 48 plus 4. And so now already answer is between 6 and 4. So I have cut down one step. I don't need 46 anymore. So you can save your time that way. You just have to reduce the modulus of the remainder. It doesn't have to be positive. So keep that in mind. Okay, so basically this is how you can find the initial solution of the Dirac-Montan equation. And then from that, I think the theory which we already studied, we know how that works. Okay, so I think I've covered everything in chapter 2 now. If there is anything left, let me know. But with this background, you can solve most of the problems of chapter 2. If you get stuck in any questions, you can post your solutions on WhatsApp. We'll take a look. So then moving on to congruences. Okay.
Sir,
Yes.
actually, I forgot to ask you last Sunday. I had one doubt in the first linear Diophantine equations in one variable.
Mm-hmm.
I thought that I think that we will have to add one case because if
Yes, yeah, you pointed that out. I remember. So I made a mistake
I
last
thought
time. No, I think you posted it on WhatsApp for me. So just to mention to everybody, I think everybody understands the trivial point, but just to make sure we are not missing anything. So you are considering the equation ax plus b, where all of them are integers, and we had considered the case. I mean, we took care of the trivial cases like what happens with a is 0 and things like that. But I think if a is not 0, I think I by mistake wrote then x is equal to b by a is the only solution. But we completely forgot that we are not dealing with real numbers. So this is only true if basically here you have to make two cases, right? If a divides b or a does not divide. So if a divides b, only then you can claim the solution set is the that b by a. If a does not divide b, then again solution set is empty. So this was the point, right? Which I think
yes,
I
sir.
missed.
Yes.
Yeah. Okay. So yeah, just everybody know this. Of course, this is trivial, but just to make sure everybody understands. Okay. So congruences. I think I kind of already gave you a soft introduction to congruences when I talked about equivalence classes and those things. So I don't want to repeat that, but just to quickly jump to the conclusion that we came back then. So we are considering the relation. So uh, let let us take some divisor and let's take it's a positive divisor for now. So we are considering the relation and we can temporarily give it some other name, but let's denote it with this symbol congruence. So this is a relation between two integers. So it is a subset of z cross z. Okay, which means that any pair a comma b either belongs to this relation or it does not belong to this relation. So such that any pair a comma belongs to z if and only if d divides a minus b, or equivalently A, B have the same remainder. On dividing by R. Dividing by. Okay. So this is what we call congruence. And here in this symbol, there is no mention of what is the modulus. So the typical way of writing this is that we write A congruent to B modulo D. Okay. So modulo or modulus is the short form of division by that particular device. Okay. So I think we already explained last time what is an equivalence relation. So I leave it for you to check that this is an equivalence relation, which means that it satisfies three properties: reflexive, symmetric, and transitive. Okay. Reflexive means that every number is congruent to itself. Symmetric means if A is congruent to B, then B is congruent to A. And transitive means that if A is congruent to B and B is congruent to C, then A is congruent to C. By the way, there is a well-known fallacy in mathematics where it is possible to give a false proof that if a relation is symmetric and transitive, then it is always reflexive. You don't need to have the reflexive condition separately. Do you know this proof? It goes something like this. So let us talk about some relation R such that R is symmetric and transitive. Okay. So symmetric means what? If A is congruent to B, implies B is congruent to A. And transitive means what? If A is congruent to B and B is congruent to C, then A is congruent to C. Yeah. But in the transitive, there's nothing which says ABC have to be distinct. What if I apply the transitive rule, assuming that C is the same as A? Now the transitive property says that if A is congruent to B and B is congruent to A, then A is congruent to A. So it seems that if the relation is symmetric and transitive, automatically it has to satisfy the reflexive also. So every relation which is symmetric and transitive has to be reflexive.
Sir.
Yes, you are.
So we could apply this to A so in the first property also, right? Symmetric property where A congruent to B, and if we assume B equal to A, then we directly get A congruent to A.
No. See, these are if A is congruent to B, then B is congruent to A. Transitive also says that if this is true and this is true, then this is true.
Okay, sir.
But then why do we have three conditions?
So you are asking why do we have reflexive as a separate condition?
Yes.
Because there is a flaw in this proof. Your job is to spot the flaw.
Oh, okay.
See, what reflexive property claims is that for every element of your set, what is that set? Doesn't matter. X is congruent to X. This is what reflexive property claims. So the proof I'm given is that so if X is congruent to Y, then by symmetry Y is congruent to X.
Sir, I think here we assume that there exists some B such that A is congruent to B.
Yes, that is the flaw. So if there such a B does not exist, then you cannot start this chain of reasoning. That is the flaw, right? So if the way the proof is this false proof is written is that if X is congruent to Y, then Y is congruent to X by symmetry. And then if this is true, then by transitivity you can deduce that therefore X is congruent to X. But this whole thing starts with the assumption that if such a Y exists, such that X is congruent to Y. What if such a Y does not exist at all? So that is the catch here. I think it would be interesting to actually construct an example of a relation which is symmetric and transitive but not reflexive. So that would be a nice homework for us to try.
So,
Yes.
but the relation is means it is symmetric and transitive. So therefore, there should be such a combination, right? Means it applies for all integers, right? That x is congruent to y.
No, but if such, no, by the way, here congruence is, you don't assume that to be the congruence notation I'm using. So it is not a divisibility wala congruence. Here we are talking about any general relation, right? So any general relation doesn't necessarily have to have every x and y pair like that.
Okay, sir.
Okay. Yeah, in the specific example of congruences, of course, it has all the three properties R, S, and T. But here I'm talking about general relations. Okay, anyway, this was just a short diversion. Getting back to congruences, so yeah, I think we all understand congruence is an equivalence relation, which means that it will split your original set Z into equivalence classes. Okay, and those equivalence classes are nothing but a set of all terms which are the same remainder modulo D. So basically, your Z can be partitioned into all the terms such as 0, D, 2D, 3D, etc. So all the multiples of D, union all the numbers which have a remainder of 1, etc. So basically, every remainder will be represented here. Okay, so in all you will have such D such classes, right? So D such classes, which the original integer set can be partitioned into. Okay. And the interesting thing is, you remember the question I asked in the problem, this practice test, let S be the set of all odd numbers between 0 and 2b, and what I had mentioned at the start of today's lecture. So you see what will happen. Suppose I construct S in such a way that it has exactly one element from each class. Okay, so it has exactly one element from the first list of items, exactly one element from the second list of items, etc. Do you see that I can write a division algorithm now for this set S, that I can claim for any integer A there exist unique integers Q and R such that A is equal to QD plus R and R belongs to S. So in the normal division algorithm, we take S to be the most boring set. It is just the 0, 1, 2, 3 up to D minus 1. So this is the standard set of remainders that we all know. In the question I asked in the test paper, I consider the set S to be the set of all odd numbers. So 1, 3, 5, 7 up to 2B minus 1. But the important thing to realize is that why did this set work? It was simply because all of these elements belong to different equivalence classes, right? So if I consider the all the remainders which B generates and write them in this way, then each of them was going to lie in a different class. Now, just to take a concrete example, so let's say if I'm talking about B is the number 5, okay, then the classes we are talking about is the first class is 0, 5, 10, 15, this number. Second class is 1, 6, 11, 16, 10, 2, 7, 12, 3, 8, and finally 4, 9, 14, all those things, right? So in the question that was asked in the problem set, the practice test, the set S would be the set of all odd numbers between 0 and 10. So the numbers are 1, 3, 5, 7, 9. And you see that all of these numbers are exactly like what I described earlier. They're all coming from different equivalence classes. So for example, 1 lies in this class, 3 lies in this class, 5 lies in the original class, 7 lies in this class, and 9 lies in this class. So each term of my set S is coming from one different bracket out of these 5. That is why that problem works. So you can generalize it to any different like crazy problem. There are multiple, basically there are infinite versions of the division algorithm which are available. We generally try to take the most simplest one where we just take the smallest element of every class, like 0, 1, 2, 3, 4, and that is the set of remainders. But you can use any set of remainders as long as they're all coming from different classes of this distribution, right?
Sir, in these sets, we should also include negative numbers, right?
Yes, we should also include negative numbers. Yes, so you have to show this both ways, or yeah. But So on the negative side, it will have -5, -4, -3, -2, and -1, things like that. Okay, but anytime you have a set S which has this property, that it has exactly one element from each class, it is called a complete set of residues modulo that. Okay, so if again, if given, so where is my pen? So if some number D is given as integer and given set S such that, so it has to have two properties. Firstly, that every remainder has to be covered. So simplest way to ensure that is the set of, it has exactly D elements, and uh, for any two numbers in S, D does not divide their difference. In other words, those two elements don't have the same remainder modulo D. Then S is called a complete set of residues modulo D. Okay. So this 13579 is a complete set of residues modulo 5, for example. And that was what that question was based on in the practice case. Okay. So in terms of congruences, like when I write A congruent to B modulo D, all I'm saying is that A and B belong to the same class. Same class that is generated by D. Okay. So these whatever 5 brackets that you wrote at the top, any two numbers of the same class are congruent to each other modulo 5. So just a different way of writing that. And the advantage is that you can do a lot of arithmetic on this, just the way we do normal arithmetic. You can add, subtract equations, multiply, and in some case divide, not always. Okay. So for example, if you try to prove this, prove that if A is congruent to B, and now let me not take D modulo N, and C is congruent to D modulo N. This implies A plus C is congruent to B plus D. I don't know, writing modulo N every time becomes a bit tedious, but I think it's good to write that as a habit. But if you just sort of ignore the modulo N part for a bit and just look at the left part, you see how it is exactly how you do normal operations with integers, real numbers. You can simply add two equations. Okay. Can you see how to prove something like this? Yes, Anushka.
So shall I tell my approach?
Yeah, sure. Go ahead.
Yes, sir. So we can represent, say, A as like n times say Q plus B.
Okay.
Yeah, and C as say n times P plus P plus D. Then when we add A and C, so A plus C will become n times P plus Q times B plus D. So n times P plus Q will be like, we can just ignore that, and B plus D will be the remainder. So A plus C will be congruent to B plus D model.
Yes, correct. So, I mean, basically, this is equivalent to saying that n divides the difference. And here also n divides the difference. So, if n divides the difference, then basically A minus B will be n times Q. Or if you just rearrange that to what we said, A is equal to n Q plus B. But I hope when you said this, right, you are not making the mistake of assuming that B is the remainder, because B can be any larger number. It does not have to be the remainder. But still, such a Q will exist, right? So,
Yeah.
I hope that part. Yeah. And the same way, you can write C is equal to n times some R plus D. And then you can just add the two together. You get A plus C is equal to n times Q plus R plus B plus D. And again, you can rearrange this back into the original form that this is nothing but n divided by difference.
And we can directly add n divides a minus b and n divides c minus d.
Yes, correct. You can directly add these two also because if n divides this and n divides this, n will divide the sum, right? So a minus b plus c minus b, which is nothing but the same thing. Yes. Okay, and I think in the same way you can see that you can subtract equations also. So instead of plus, you can have minus in both places. So a minus c and b minus d, that also works just fine. Okay, and you can multiply also. So if a is common to b and c is common to d, then ac is common to bd also. And why is that true?
So we can multiply the equations like represented in that like a equal to n q plus b from, and all the terms that contain m will come under one term, and the remaining will comes out to be that
Yes, correct. So when you
AC
multiply,
congruent to b.
correct. So when you multiply these two, right, you'll get AC is equal to something complicated, like the things will cross multiply. But out of all that cross multiplication inside the bracket, you'll basically get n times something plus BD, right? So once you have this form, this implies that n divides AC minus BD. Therefore, AC common to BD modulo n. Okay, does everybody follow this? So you see how powerful this is, that you can add, subtract, and multiply just like normal equations. And you can take powers also, like basically if a is common to b, then a raised to something, a raised to k is also common to b raised to k mod n. Okay, so you can multiply the equation with itself. Similarly, you can add the equation to itself. So if a is common to b, any multiple of a is common to multiple of b. So k times a is common to k times b mod n. So now the question is, can we do the reverse? Suppose given some integers such that k is congruent to kb. Can we say that, is it true that a is also congruent to b? In other words, can we just cancel the copy of k from both sides?
No, sir.
No. So in general, you cannot do this, and you can, I think, come up with some simple example why this does not work. So for example, maybe 2 is not congruent to 4 modulo 4. But if I multiply both sides by 2, I'll get 4 is congruent to 8 modulo 4. So I cannot cancel a copy of 2 from here to get this one. But in some cases, you can cancel the copy of k. So what can be that condition when it is safe to cancel k?
So
and
if
when
n
you
is
cannot?
prime,
If n is prime,
No, sir. Still
uh,
we can't cancel.
then we can't cancel, right? What if k is a multiple of that prime number?
N and k should be co-prime.
Right. Yes.
Right? N and k should be co-prime. That could be the condition. But see, how we can deduce this? Like, suppose we don't know anything like that. How would you start analyzing this? That so from here, what we can write, because this is given, we can write n divides k minus k. So therefore, n divides k times a minus k. And now you can see that you can apply Euclid's lemma here, because from here I want to make the jump that n divides a minus b. So what can be the condition if something is true? Then I can apply Euclid's lemma to go from here to here. So that condition is n and k have to be co-prime, right? So if n and k are co-prime, GCD of n of k is 1, then it is safe to say that n is dividing a minus b. Okay, so if k common to kb and n are co-prime, then I can make this clear. Okay, jumping ahead a bit, but I mean, just the way we are asking the question, when is it okay to cancel a copy of k like this? We would also want to think of the question of what if a raised to k congruent to b raised to k modulo n? Does that imply a congruent to b modulo n? or what is the condition which these numbers have to satisfy for something like this to be true? So right now we don't have enough theory to answer this question fully, but just give it some thought at the back of your mind that this is also something that we need to think about. But in general, we cannot do this. So hopefully you don't make that mistake in the paper by just canceling K here. Okay, so then it's good that we can use congruences for a lot of these things, but now to come for some practical applications of congruences. So one important thing that congruences can help us is to find simultaneous equations of multiple such congruences. So you may have encountered these questions in Praveen and Sanya also, like find the smallest number which leaves a remainder of 2 on dividing by 3 and some remainder of 5 on dividing by 7, something like that, right? So if that can be expressed as a congruence equation, it may look something like this: that find the number z or x such that if I divide it by 3, I get a remainder of 2. And if I divide it by 7, I get a remainder of 5, something like this. So if you want to find such a value of x, what you can do. So I think this is a small numerical example, so you may be able to find some answer just by trial and error. But what can be the systematic way to solve such a system of equations? So that is what we want to do ultimately. So that is called a Chinese remainder theorem. So the Chinese remainder theorem deals with the solution for such a system of equations. So x is common to a1 mod b1, a2 mod b2, etc., etc. Then in what conditions such a system of equation has a solution, and what is the complete set of such solutions? So that is what the theorem talks about. We can start by trying to handle the simplest case. So let's say we have only one equation. Okay, so let's say we are only dealing with one equation where suppose we are given a1, b1, and d1. d1 not equal to 0, and so solve the equation. I'll drop the subscript also because there is only one value, so I can just call them a, b, and d. So solve the equation ax congruent to b modulo d for x being an integer. So the question is same as what we did earlier. Right? When we said solve ax equal to b, we have to come up with what is the complete solution set of this equation. Okay, so how do we approach this? Yes, Raghav.
Yes, so by like the definition of congruence, we get that dn is equal to ax minus b for some n in integers.
Yes.
Then we get ax minus dn is equal to b, which is
Yes.
a Diophantine equation. So we can just solve this equation.
Yes, correct. So here x and n are the unknowns. So when will this set of equations have a solution?
When
Oh,
GCD
sorry.
of A comma D divides B.
Yes. So if the GCD of a comma b, a comma d divides d, then this will have a solution. Then a solution exists. And if that does not happen, then there is no solution. So assuming that that is true. So assuming that this is true, then what could be that family of solutions? Sorry. So we know that the Diophantine equation itself has an infinite family of solutions, right? So if there is a initial pair, so maybe let some x naught comma n naught be an initial solution of this equation. Then, so which means that x naught is a valid solution of the original equation, right? So what will any other solution look like? If you remember the adjustment that we are able to do. So we have to increase x naught by some amount and decrease n naught by the same amount. Yes, Raghav?
Yes, it will be in the form of x naught plus dk for some k integer.
Yes. So x naught can be replaced by, it can be added with any multiple of, not d actually, this a comma, the GCD of a comma d, that is what matters, right? So
Yes.
if the, so let us call that GCD as g. So let the GCD of a be, as g. So basically that GCD represents the smallest step that you are allowed to take. So you cannot take a step smaller than the GCD. So therefore you have to have so any k times the step of the size of g, or not g, sorry, I think b upon g, right?
Yes, sir. D upon G.
B upon g, sorry. And in the same time, n naught has to be reduced by the same amount. B upon g. Okay, so we are adding this term on the left side and subtracting the same term. And so when you multiply this with a and this with b, I don't know about this, pen is really bad. Sorry, actually I reset my tablet to factory settings, so all of my settings have gone away. So if I multiply this with a and this with d, and when I add it together, this term will get cancelled. So, so basically, the entire family of equation. Finally, we are interested in finding the equation of the original congruences. So, what is the sort of distance between two consecutive solutions? So, here, if I set k equal to 1, that will give me the this distance. So, from x naught, the next solution is x naught plus d by g. So, this d by g represents the step that I can take from one solution to the next of the original equation. So, in other words, if ax is congruent to b modulo d, so if ax is congruent to b modulo d, then the next step is x which is added with d by g is also congruent to b modulo d. Okay. So therefore, the solution set of x is turns out to be nothing but the set of all such equations. So solution set of x is nothing but the same set, x plus k times d by g, where k is any integer. Okay. And the whole thing is reversible. So the fact is that this equation is true if and only if this is true. So there is no step in between where there could be a change in the solution set. So that is why it is enough to say that the solution set of the new equation is the same as the original one. Okay, so this is
In
how
the
we deal with.
solution, so in the solution set, it should be x naught, right? Because
Yes, where x naught is the original initial solution. So in terms of, so this can be the step that we can take d upon c. But at some point, because the original equation is modulo d, so this will be periodic, right? So if you keep taking d upon g size steps, how many such steps can you take before you will basically be cycling over the same set of remainders? So by what that I mean is you start with the first solution is x naught. So next solution is x naught plus d by g. Next solution after is x naught plus 2d by g, etc. At some point, you'll basically exactly after g such steps, right? So when you finally go to x naught plus g times d by g, this is nothing but x naught plus d. So modulo d, we have come back to the original remainder because x naught plus d and x naught will have the same remainder, modulo d. So the number of, so this is often what we try to look at. So the number of unique solutions modulo d. So what is the number of unique solutions modulo d? I hope you understand what this means. That if there are two solutions which have the same remainder modulo d, we don't consider them to be distinct. So this number is nothing but g, which was the GCD of the a comma d. Okay. Okay. Maybe for clarity, we can take some numerical example also. So let's say take a equal to, I don't know, 10 and d equal to 15, for example. Okay. So let's say the equation is 10x is congruent to 5 modulo 50. Okay. So I've deliberately taken 5 here. So all of us understand instead of 5, if I had taken something like 4, then this solution will not have any answer because the basic condition. So the GCD of 10 comma 15, which is 5. So 5 has to divide this constant term. So 5 does not divide 4. So then this will have no solution. But so therefore, if you take the equation 10x is common to 5 mod 15. So what is the first solution of x which satisfies this equation? So for example, x equal to 2 works, right?
yes, sir.
X equal to 2 is the first solution. And then from this point onwards, you can keep adding d upon g. So d is so 15 upon 5. So if I keep adding 2 plus 3, 2 plus 6, etc. So I can keep doing this and I'll get 5 such discrete solutions. So basically 2, 5, 8, 11, and 14. These are all the solutions I'll get for x. And after that, the next solution after that is 17. But 17 is the same as 2 modulo 15. So it's not really considered as a new solution. Okay, so this was how we deal with a single equation, single x common to b modulo b. But now for Chinese remainder theorem, we want to deal with the entire family of such equations. Okay, so now let us say that you are given a1, b1, d1, and a2, b2, d2. Okay, all of them are integers and d1, d2 are non-zero. So we are now want to solve the equations a1 x congruent to b1 modulo d1 and a2x congruent to b2 modulo d2. So X has to simultaneously satisfy both the congruences. So again, we have to conclude what is the necessary and sufficient condition for this to happen and things like that.
Sir, one of the conditions is that they must be individually solvable.
Yes, correct. So because each of them is a single variable, like single equation from the previous example. So therefore, basically, GCD of A1 comma D1. So GCD of A1 comma D1 has to divide D1, and GCD of A2 comma D2 has to divide D2. So do you think that if these two conditions are met, then the family as a whole will also always have a solution, or may not be true? There could be some cases where individually there is a X which satisfies first equation and X which satisfies the second equation, but not possible to have a simultaneous solution. Could that happen?
Yes, sir, it may happen.
Hmm. Why could that happen? Like what could
Sir,
be
for
the
example, 2x is congruent to 0 mod 5
Mhm.
and maybe we can say and 2x is congruent to 1 mod 5.
Yes.
Both are individually solvable.
Yes, correct. Okay, this was, I mean, a very straightforward example where I even to take one number that let's say A1, A2 are the same, D1, D2 are the same, but B1, B2 are different, something like that. So that will trivially have no problem. But more in general, what could be the condition where the problem like this can arise? So you can think of it in this way, what we did just now. Basically, what is the stride of the two equations? So let's say these two conditions are met. So there is some initial solution x naught, let's say for the first equation. Okay, let me call it x1 actually. So let x1 be an initial solution of the first equation and x2 be a equation, solution of the second equation. Then we know that this is basically an arithmetic progression of all the values which the first equation is satisfied, right? X1 plus that whatever uh, d1 by g1, x1 plus 2 d2 by d1 by g1, etc. So this is an AP. This is also an AP, d2 by g2, etc. So if these two APs have any common term, then we are done. But as the one example which Aranav pointed out, quite possibly the two APs will never have any common term. And there are more non-trivial examples also where not necessarily that two APs will have a common term. Okay, but anyway, I think we are almost out of time, so I'll let you to independently explore this. So try to solve the two variable problem completely or two equation problem completely. And then once you understand how that works, we can try to see how to generalize this for any n equations at the same time. Okay, so that is what the Chinese remainder theorem gives you. And that is just one of many useful ways where congruences can be applied. So we'll lot of the number theory is going to come ahead, like Euler's theorem, Fermat's theorem. All of that is based on congruences. So this is one of the most powerful tools that we have to deal with. So that is why I'm covering it first, even before prime numbers. Okay, so we'll continue discussing on this ahead. Already, I think you have some homework, which is you want to completely solve that PQRS problem. Why is the converse true? Like if PS minus QR, I mean, if PS minus QR modulo is not one, then why is that GCD condition not true? So that is what we need to find out. Okay. So in the next 10 minutes which we have left, I just want to complete the puzzle which has been ongoing for the last several lectures, which is the how are we encoding symbols efficiently. So I think last time we already came up with one scheme where we talked about what is called prefix free codes, right? So if taking the same example as before, let's say we have 1,000 character text file containing the letters A, B, C, D, which we want to send, and let's say A occurs 500 times, B occurs 250 times, and C and D occurs 125 times each. So we already said that with the fixed length coding, if I give the fixed symbol to each of them, then how many bits will I require? So in fact, I require 2 bits per symbol on average, right? Because my total file size will have to be 2000 bits. So I have to send 2000 bits to send this information. But with the prefix free code that we had come up with last time, where we said, let's say A is given 0, B is given 10, C is given 110, and D is given 111. So now we can compute with this scheme how many bits will be required to send. So A requires only 1 bit per symbol, so one. And there are 500 such symbols in the original file. So A into 500 is I require 500 bits in order to transmit A. B has 2 bits per symbol, and there are 250 such symbols to be sent. So this is our 250. So C and D in fact require more bits per symbol than the average. So each of them require more bits, but the number of times they occur is less. So their total sum. So if you add up all of this, what is the total size of the file that you have to transmit?
So 1750.
1750, right? So you see your original file was 2000 bits, but now we're able to send only 1750 bits and transmit the same information. Okay, so that is what this code is achieving. So this is an example of what is called the prefix free code. And actually, most people call it prefix code, but I like to call it prefix free code because doesn't have prefixes. So it's like calling it prefix code is a bit misleading. And so this for this, the important thing is how to build such a code. So that is something we did not discuss last time. I just gave you this code here that if you use this scheme, we were able to verify that there is no issue with the prefixes and we are able to save the bits. But how to actually construct such a code if you know the distribution of the bits? So if you know what is the frequency of each character, then how can you use that information to construct this code in particular? So that's what I want to show today. Again, this is not the only way to do it, but this is one of the most easy way to do it. And what you do is basically, let's say you start with the original this ABCD. And okay, before that, I think I'd also shown the sort of tree representation of this, right? Remember, basically, you have a tree of possibilities where at every step you go left or right, and basically left. If you go left, you are going to 0, and if you go right, you are adding a 1. So that is how this became 0, 0, 0, 1, 1, 0, 1, etc. So we want to construct this tree and place these symbols at various nodes on this tree. That's what we want to do. So the way we do it, we actually start from the lowest probability symbols. So in this case, for example, C and D have the lowest probability, right? So what I do is I want C and D to be the leaves of some tree. So my eventual graph should look something like this. That C and D are both the leaves of some common point. So 500A, 250B. Okay. So I've already combined C and D together. So you can imagine that this is a new symbol that I'm dealing with now. So instead of writing ABCD this way, I am going to now write A is occurring 500 times, B is occurring 250 times, and this combined C plus D symbol is occurring 250 times. Okay, because they are going to add them together. And I can keep repeating this process. Now, what do you see? What are the these occurring events?
C,
B and
B and
C
C
plus
plus
D.
D.
So as a next step, I have to connect these two together like this. And so now at the last step, I'll have 500 times A and 500 times this B plus C plus D. So therefore, I connect this like this. So this is how I can build a tree. And once I've built the tree, I just can start assigning values to that. So if I think this whole thing, I mean, I didn't show the last step here. Actually, we have to connect this together also one last time. So basically, then the tree looks something like this. That A is in this direction. So, oh, sorry, this is not what I So this is what your final tree looks like. Okay. So you have connected the B plus C plus D and A also with a common root node. Okay. And now with this, you start assigning the labels. So if you call the common root node as the empty set, so the common root node does not have any representation. Then, for example, we have understood convention left is 0 and right is 1. So following that, I can assign 1 to A. Then this node, which will assign the 0, but not assigned to any code. Then from here, I can call B as 0, 0. This node will be 0, 1. C will be 0, 1, 0, and D will be 0, 1, 1. So that is how I constructed my code. A is 1, B is 0, 0, C is 0, 1, 0, and D is 0, 1. Okay. So by the way I constructed the tree, do you see that it is guaranteed to be prefix free? See, when will a prefix occur? If there is let's say some part of your tree where starting from the root node, you first encounter some character, let's say A, and from that you continue to descend to some other character B. If that happens, then clearly the code of A is going to be a subset of the code of B. But the way we have constructed the tree, you are always going from leaves of the tree to the root of the tree. So this will never happen. Okay. So that is why this construction is guaranteed to be prefix free. I have not given the proof of why this construction is guaranteed to be optimal yet. That will require some more advanced theory, and which we don't know honestly. So this topic is by the way taught in third year of engineering in IIT, and probably in most entrance or most engineering courses in electrical engineering. Okay. So I'm trying to simplify something that we are going to deal with much more formally. So there will be a lot more formal notation to define all the things, but the logic is simple enough for everybody to understand. Okay. So maybe just to conclude, what is the practical use of this? Of course, we are saving some bits over here. So the fact that the file of 2000 bits went down to 1750 bits. Prefix codes are used pretty much everywhere. So we are in a Zoom meeting right now. So your camera is capturing data from your environment, transmitting that over the internet. You can calculate if you want to transmit HD video at 60 frames per second, how good your internet will have to be. And realistically, nobody has that good internet. But the fact that Zoom still works is because some compression is happening. Your computer is compressing the data from your camera into something smaller and then sending it to my computer. And my computer is decoding that back into your image. So all of that happens because of compression. But there are some other places also where you actually require prefix code. Can you think of some place where you require prefix code in real life? Why would you require prefix code in real life? So, for example, you know Bhaskar Sir Pratishthan, their phone number is +91 02025434546. This used to be the number of Pratishthan. This is actually a kind of prefix code because the thing is, this is the country code of India. This is the STD code of Pune. And if you check the list of ISD codes, there is no country whose international calling code is +9, or there is no country whose international calling code is +912 or something like that. Because if that happens, do you see there could be ambiguity? Suppose I give you the phone number +910205434547 without adding any spaces in between. How do you know that this is a number inside India or some other country's number which starts with +9 and this one? So the only way this ambiguity is avoided is that what is called the ISD, the international, I forgot the full form of SND, but the ISD country codes assigned to all the countries in the world are prefix-free codes. This is how you don't require to add space in between to guarantee that there is a unique way to decode that particular phone number. And the same thing is done with by every country. So all the STD codes in India, they are all prefix-free codes. So there is no other city whose who code goes like 0207 something something, because again that will create ambiguity. So at every level we are ensuring unique decodability through prefix-free codes. And this is just one example. I think if you check how postal service assigns their area codes and things like that, you will find many more examples of prefix-free coding. Even like any book that you buy, you know that the back your ISBN code, which uniquely identifies that book. So that ISBN code is also prefix-free code. There is uniquely one way to decode that into the category and subcategory and things like that. So this is just one example of prefix code in real life. Uh, so hopefully, I mean, the motivation to share something like this with you is to give an idea that if you decide to pursue something like engineering, electrical engineering, or computing, this is some of the mathematics that you will be dealing with at in those branches. In fact, one thing I would like to do is that invite different people from different streams to share their experience with you, so that you get a better idea of like what is it that interests you. If this is something that interests you, then you will choose a different kind of mathematics to study. If something else interests you, maybe matrices, calculus, that will lead to a different field of engineering. So every field has its own set of sort of things that you require to study for that. So like giving you exposure to various domains like this is useful from that aspect as well. Okay, I think we're almost done, so we can stop for the day. Thank you. Bye.
Thank you, sir. Thank you, sir. Bye.
Bye, sir. Thank you.
Thank you.
Bye,
Sir,
sir.
bye, sir.
Thanks.